So I wanted to talk about something that I found recently that I hadn't realized, but has been hiding in plain sight all along. It's about meaningful complementary orientation types in geometric algebra. So we've seen this morning when I talked about the classical mechanics that if you have a line in 3D, sometimes it can be an axis, a thing you turn around, and sometimes it can act as what some people call a spear. That's one of those momentum lines, a line you move along. And the two, as we saw this morning, are dual to each other. And this mixture of associating an orientation in a plane with a vector perpendicular to it was something that we have tried to avoid for a while. George W. Bush even called it the axis of evil. And since then, of course, we haven't tried. The same thing you have in 2D PGA, the plane-based geometric algebra. You can use the normal vector of a plane to distinguish what you consider the object side and the space side of the plane. But at the same time, it is sensible in planes to have an orientation that indicates whether you want to put a picture in mirrored or not. And even in 3D CGA, there is Dutch cheese, which is real cheese, and there's anti-cheese, which is made of holes, where again, the direction of the normal indicates where the cheese is, but still you can also orient spheres on their surface with a left-handed or a right-handed orientation. So there are two types of lines in 3D, these meet lines and these join lines, and we really want them both. I think I showed that this morning. And in 2D PGA, one of them becomes a rotation center because it's the meet of two lines in 2D, which are hyperplanes. But the motion line remains in any dimension, a line a point moves along, so it always remains something that we would now describe as a dual bivector. How would you distinguish these things? Well, as I said this morning, as far as I'm concerned, the constructive property of geometric algebras is their symmetries, their reflection symmetries. So we just have to see whether they're really different when we reflect them in, for 3D plane-based geometric algebra, the Euclidean geometric algebra in a plane. And you see that when something is rotating counterclockwise and I reflect it in a plane, it's still rotating counterclockwise. The axis doesn't change when it's perpendicular to the plane. But when the axis is lying in the plane and it rotates this way, then its reflection is rotating the other way. But the opposite happens for the lines that are spheres, that are pointing out of it as a motion direction. If I now reflect this pointing out line in this plane, then its direction reverses, whereas if it was a motion line in the plane, it would not reverse. So these are two different properties of the different types of lines. And classically, people have been using polar and axial vectors to distinguish that. We've seen this morning that we prefer not to do that. We don't need to. We use the bivectors and the dual bivectors. So we're going to have to talk about signs under reflection. And I gave this talk separately. So here's this thing again, what we had this morning, that in geometric algebra of vectors, a reflection of a vector x in a plane with normal vector a is one of those sandwiching products. And you see that there's automatically a minus sign involved. So if we're going to have to be careful about minus signs, we should not count these because they're just part of what is a reflection operator. And if we have multiple reflections in multiple planes, then these minus signs accumulate. If we want to reflect something that is itself the product of a number of vectors, then I also get signs from that. So I have here in David Hestenes's notation of how to apply a versor to an object with an underscore, the default operation that is just reflection, multiple reflection of a general object in a geometric algebra just has some minus signs. So let's ignore those. Let's give this as a notation for this in shorthand. There are signs in there and they are confusing, but we're hiding them in our notation so that the real signs that occur when we want to distinguish these two types of orientations will be explicit. Now, we've been a bit sloppy with how to associate one of those rotation axes with a rotation plane. We've always implicitly used the duality that we had in the space to do that. And that means that we cannot change these things independently. Whereas in that first slide with all these pictures I showed, that sometimes you want to say that the front and the back of a plane are different, and sometimes you want to say that the orientation is different. So we would like to have independent control of that. But it's certainly true that this picture gives a clue as to what you should do. So here we have the midline of two planes, which it's from the yellow to the green plane. So or from the green to the yellow plane. So it has an orientation that is like this. Here we have the normal vector of the green plane and the normal vector of the yellow plane, which will also turn in this way. But we also know that if we do something like a cross product, which is the dual of this operation, I get something that is outward pointing as that relationship. Well, what happens when we do reflections? We know what happens to the pseudoscalar, which is the volume element of the space. If I have a versor made of an even number of reflections, it doesn't change. If I have it of an odd number of reflections, it does change, because this is just the determinant of V times the volume element. So that means that if we have an element that is dualized, that involves the use of a pseudoscalar, because it's the orthogonal complement, then we automatically expect one of those signs to appear, relative to if I first reflect the object and then dualize it, because the dualization involves this pseudoscalar. Well, that's precisely the sign we were looking for to characterize that difference between the extrinsic, the pointing out characterization, and the intrinsic, the in-plane orientation. So we're going to try to support the claim that these complementary orientation elements are actually each other's dual. So that means that we get a different meaning for dual than we had before. We originally saw it as just another representation of the same element in a representation that allowed us to swap wedge products for dot products. We are now claiming that they're actually different geometrical elements if you pay attention to the orientation. And we're going to try and see whether we can carry that through consistently. The depiction you would give of that is that in the plane-based geometric algebra, if I have a plane sticking out in the direction E3, so that's a plane that looks like this, I just had to do that, then that is an extrinsic plane with a normal vector that says, this is the outside and this is the inside. And we would then say that the dual of that is something that I'm going to interpret as that same plane, but now with an orientation on its surface. But if you compute this dual, and we'll see, I'll use the Hodge star, which I'll explain a slide later, then we find that this is actually closely related to the line, the extrinsic line, a line around an axis that points in the E12 direction. Algebraically, these two elements are each other's dual in this algebra. But we, of course, also want an intrinsic line in that E12 direction. So we would indicate that with star E12. But if we compute that algebraically, we actually get this element. So you see that we have a bit of a dilemma. We want each of these elements. We see that the symmetry of these two are very closely related, and the symmetry of these two are very closely related. We want to make a distinction between something and its dual, but we don't have more elements in the algebra than we have to represent, E1, E2, E1, E2, E3, etc. So we have to going to find room for these elements. Just a little bit about the Hodge dual. Since I will be working also in the plane-based geometric algebra where the pseudoscalar is not invertible, I cannot just do what we always do and say the orthogonal complement is the element divided by the pseudoscalar. Hodge dual is a very ugly type of dual. You define it on coordinates and you say, if I want the dual of this element E12, then I would just find which element I need to add to get the pseudoscalar of the space I'm interested in, which in this case is E123, and that is the element E3, so that's the dual. And then you extend that by linearity to something that is a sum of these basis elements. At the end, we will have a nicer dual after a suggestion by Charles Gunn. But this is the regular dualization that you also know from crystallography and physics, where points at a certain distance are dualized to the plane in 1 over the distance at the other side of the origin. And this is a little computation. I won't really, the things I will be saying will apply to any of the duals. I have used in the write-up the Hodge dual just to be specific, but I'll leave that at the end of this talk. And of course, always with duals, there's some care required, especially if you pay attention to signs of orientations, because the undual is not just doing the dual again. If you're sloppy about signs, it is, and otherwise you have to be take more care. But we're not going to do much of that either. So let us look at a simple geometric algebra, RD. So R3, for instance, the geometric algebra of 3-dimensional space. Now, since we have denoted the planes in which we reflect by their normal vectors, we should really say that this is a space in which normal vectors occur. And the only operations, the only verses I will have is to rotate these normal vectors in an arbitrary direction. I can intersect these planes by taking the wedge product of the normal vectors, and then I get a line through the origin. So all I get here is things that rotate around a fixed point. The verses are multiple planar reflections, and they are rotations. And well, all of us know and love the fact that in 2D you just get the complex numbers. In 3D you get quaternions, and in DD you get sort of spinner-like objects that rotate around the origin. It's useful because it's a sub-algebra of all useful geometric algebras, really. And let's now check that these earlier pictures that I had indeed work in this thing. So if I apply E3 as a versor to this element E12, which was an element that is the midline of a plane that rotates from E1 to E2. So it's a plane in a certain rotation. So it's a line in a certain axis rotation. Then indeed I see that it transforms in the proper way. Whereas if I had an axis line lying in the plane, then it would have changed sign. And the other type of line that we were also interested in would be the dual of this thing. Well, I now have to apply my transformation rule that I'm going to say that if I want to transform the dual of something, I can transform the thing itself, dualize it, but I may have to add a minus sign if it's a single reflection. And that's precisely what happens. And I indeed get the right arithmetic, the right algebraic results for the things that I geometrically wanted. And then, so the most easily visualizable things in this small algebra of hyperplanes around a point is just E1, E2, and E3 in the different coordinate directions and their duals, which are the intrinsically oriented ones, and you get the axis lines and the spear lines through the origin. Yes, you can also do something about the point at the origin, which is E1, 2, 3. It's the intersection of 3 planes in the origin, and give that an extrinsic orientation or an intrinsic orientation. But I must say that I find these very hard to visualize and very hard to use. We need to understand a little bit better for this to be a useful visualization. And the same thing about the volume element of the space. But in my visualizations, I will usually focus on these. And then we get that same picture that we saw before, where the elements we're interested in are indeed all present, but there is this awkward equivalence that star of E12, if I were to compute it, not just leave it like this, I would get the other element E3, which has the same geometric symmetry, but I wanted them both and I wanted them separately in my software. If we look at the plane-based geometric algebra, to correct my mistake of this morning of calling it projective geometric algebra, then those are That's the algebra of the offset hyperplanes. We've seen that a little bit this morning. There's an hyperplane at infinity, which is that E0 element. And now I get generally affinely offset subspaces from the origin of any dimensionality. We have talked about this morning. I can do the same sort of visualization there. And I see that the earlier algebra that I talked about of the algebra of normal vectors is a subalgebra of it. So that part of it doesn't change. But I get these new things that involve the hyperplane at infinity with the, you know, the directions being ideal points at infinity. And probably, so I have depicted that here by a gray sphere, which is supposed to be very far away, the celestial sphere with a point on it. And you can see that corresponding symmetry happens between these things. The most useful one is probably something like this, which is the axis of a translation. The axis of a translation is in the vertical direction is infinitely far away in all directions, so that as soon as I start turning, a point here gets boosted up. And that is precisely dual to the other element, which is E12, which is dual to this one, which is actually following the point that is being pushed up in that direction, which is the star E12 element. And so the algebraic interpretation can be made, and you can learn to think in these elements. The dual of this thing, this is a translation axis at infinity that helps me boost my things with a linear momentum in the vertical direction, is an ideal rotation orbit at infinity, which will make anything in finite space turn. And this is precisely where this angular momentum part resided this morning. Anyway, we now in this extended algebra get that there's a different fourfold relationship. I still have E12, an axis around in the E3 direction. So the plane E1 turns to E2. I have its dual, which is the movement along that line. But now this dual, if I compute the Hodge dual, becomes this element, which is indeed the thing that, you know, is the counterpart that actually provides the motion that moves in this direction, whereas this is the axis that provides, no, this is the axis that provides this kind of a motion. So all these things are consistent. You can work with them. They do seem to supply some things that we want, and you can do the similar kind of thing in the 3D conformal geometric algebra. But again, you sort of have twice as many elements as you have room for. Can we combine these elements? How am I doing on time? Okay, all right, should be enough. We'll stop here for now. Yeah. Oh, that's why you were getting up. I meant we can go to other algebras, but the same phenomenon occurs again and again. So you do seem to need twice as many elements as you have available, and we're going to have to do something about that. Well, one of the interesting questions we can ask is what happens when we combine elements? And we know that if we do an intersection of things, which is in the algebra of normal vectors is denoted by the wedge, it's not a span now, it's an intersection, then it has the nice property that when we apply a versor to these things separately and combine them, it's the same thing as combining the versor to the combined result. So it's a nicely equivariant way of talking about constructions. We have a problem with the join. Normally the join is defined as dual to the meet, and this we're going to have to be careful about that now. So if we take two elements and we wedge them together, and we say the dual of the join is the join of the duals, and you would execute that on 2 points from, for instance, this plane-based geometric algebra, then what you find is that this has been especially constructed to take something that was in the space of intersection of three planes joined with a point a little bit further away. You do the whole computation, you get a result here, you do the dualization, and then you have to, at the end, undualize, you bring this one to the other side. And what you get is something of the same orientation type. So I started with a point, I have another point, I make the line that I want to be a join line connecting one to the other. And what I do at the last step is to say, no, I'm going to make it an axis line again, because I want to end up in the same algebra that I started traditionally. Well, it's clear that if we want to be more careful about these two complementary orientations, we should really not do that last step. We have made the join line and we shouldn't go back and make that an axis. So I found it handy to define something for which I couldn't really find a suitable symbol, but I've made it look a little bit like a join, which is something that doesn't go quite as far. You do indeed the wedge of the jewels, but you stay in that jewel space because you've now joined these points and you now have an intrinsically oriented line, and that's what you wanted. Interestingly, something that I messed up with quite a bit in the past is that I always thought that the join was a tidy operation and that it would act like an automorphism, just like the meet. But it's not, because if you count how many dualizations there are in there, it's an odd number of dualizations, so that you would always get a determinant and your sign would swap if you do a reflection on that. Because we have an even number of dualizations now, that doesn't happen here. So this is really a tidier operation, but it takes us from these two extrinsically oriented elements to something that connects them, which is an intrinsically oriented element. And so again, we get fourfold relations. If I now say I have a plane with normal vector E3 and I want to intersect that with a plane in normal vector E1, then the actual axis that you get that represents that is the shortest path in which you can rotate this around that and their common geometry. If I do something like this, this looks very much like it could also define a rotation axis. Here I have an intrinsically oriented plane that I want to bring into coincidence with another intrinsically oriented plane. Well, obviously I can do that also by a rotation axis that works in the same direction. So here I have two related things, one in the dual space, and that pops me back into the extrinsic, the axis space. And here one that stays in the axis space that gives the same result. And if we dualize these relationships, so instead of E3, we look at E12 and E23, then we find something similar there. This looks much more like how we are normally used to representing the wedge operation. You have a vector in this direction and you wedge it with a vector in that direction, and you get a plane that is intrinsically oriented in that direction. But again, just by the same token, I can take an axis with a specific orientation, rotate that to coincide with this one, and what I will have made is something that is an object that has that intrinsic orientation in this direction. So there is an, yeah. Okay, well, who do we believe? You of now, or you were 5 minutes ago? It'll be enough. Now, but there is something strange going on. If you have observed what I've done here, then sometimes I explicitly compute the dual, and sometimes I use it as sort of a symbolic notation of consider this object as an intrinsic element. That is worked out here. In my experience, well, just that it makes a difference what you do, and you get completely nonsense if you had first, I'm taking a reflection here in an offset plane of a plane, and it should just move up. And if the orientation of the original one was like this and it's reflected, then it should end up in that place like that. And if it was intrinsically oriented, then it should end in this place like that. And it does if you don't interpret that dual as an instruction to go to the dual, but to interpret it as a dual element. But if you actually use it as an instruction, it goes wrong. Again, it's because we have too few elements. And on the last slide, I'll show how to resolve that. I did wonder why we didn't encounter this before. And if you really look at what we usually do is that we don't use reflections that often. We mostly use even verses and the motions that are encountered with that. And if you then see how these formulas simplify, you see that this thing just transports to where you want it to be without any signs. And whether you first decide to consider it as an intrinsic element and then transform it, or first transform it and then decide what kind of element it is, it makes no difference to your computation. And that's why, we didn't really care. But as soon as you start becoming serious about reflections, the differences appear, and it really makes a difference what you do first. So we do want both complementation types because we've seen uses for them. Dualization does switch the type. We have seen various fourfold relationships between those primitives, both in their relationships. I've defined a sort of a new combination that uses this more consistently or more explicitly, but I get twice as many primitives to describe the world. So somehow it should cost twice the space. I just don't have the elements to place them. The important thing for implementations is that you don't have to implement a whole new algebra to compute with these implicit versus extrinsic elements, because you can make one out of the other by just transforming them and maybe changing a sign or not, depending on whether you have a reflection. So in an object-oriented software, you can overload these things. And in fact, we didn't realize that there was this essential difference when we implemented the simulations that you've seen of the classical mechanics that I showed this morning, because as you're constantly aware of what you're doing, it seems to be fine. It's just when you want it to be very explicit what you have to do that it turns up. Now, what I have since found is that there was a suggestion by Charles Gunn, who was in this. He sees the plane-based geometric algebra as a projective geometric algebra. In projective, you have a dual space. And he always said that objects can be represented either in the plane-based space or in the point-based space, and this is the same kind of object. I think we now know that if it's a dual space, then one of the spaces represents the object in an extrinsic orientation, the other space represents it in the intrinsic orientation. But he showed that it's better to keep tabs on these two spaces, to keep them separately in your notation. So he suggested a notation where you go from downstairs to upstairs indices rather than this dual that I showed. So from E01, you do not go to E02, but you go to E23 upstairs. It turns out that that becomes a dualization that's not dependent on the origin, while the Hodge is. So it's much nicer. And so in fact, he has the algebra for the geometry that I found, and it would be nice to combine them. This actually can be explained better by something that Anthony showed in 2010 in a paper that he did in ICACGA, in which he showed what's actually going on. If you embed the PGA, which its sole use of Euclidean elements and the elements at infinity, to make the planes. If you embed that in the conformal geometric algebra, and then you take the conformal dual, and on the other end, you get flat elements that contain the point-based algebra. So rather than this awkward dual that we have here, if you embed both of them in conformal geometric algebra, you clearly switch from one to the other, and the whole thing becomes a lot more symmetrical. Our argument at the time to Charles Gunn was, if you use both of them anyway, why don't you use conformal geometric algebra? Because you then also get spheres and circles. I now understand better why the problem doesn't go away. If you still want to talk about cheese and anti-cheese, then yes, cheese and anti-cheese, then you would also want to double the conformal geometric algebra and keep it and its dual. So the fact that you can nicely represent the things and their duals in the conformal geometric algebra as a subalgebra is a nice advantage, but you don't need to encode it that way. And that's where it stopped.
We have time for one question. John.
Uh-oh, Joan Lazenby.
So Leo, how does this relate to what Jonathan Cameron did many years ago for oriented CGA? So, you know, he took Stolfi and effectively.
So if you have oriented CGA, if he was capable of both independently switching what he considers inside and outside and the picture you draw on the sphere itself, then it would be the same. But if you compare what I've done here to, for instance, the oriented projective geometry that Stolfi introduced, then he still makes the equivalence. He doesn't really distinguish between intrinsic and extrinsic orientation. He just keeps track of what happens to orientations when you do transformations.
Okay, right.
So it was an additional subtlety that I hadn't quite realized, and it does necessitate some doubling. But you know, you could also not care, because like I said, if you have just even versors, so the motions, you can decide before or after whether you want to consider this as extrinsic or intrinsic, because it won't change. It'll transform properly. And that's possibly why I didn't see it before.